Everybody, welcome back to the unofficial Handmade Hero Mac OS platform layer tutorial. My name is Ted. It's a beautiful day here in Park City. I'm having my coffee. You can see my little moose behind me. It's almost snowboarding season, so I actually went yesterday, hiked up Alta and took a run with my friend Ben. Pretty awesome experience. Highly recommend. Let's see. Yesterday we wrapped up the start of audio. So what we have is the audio kind of response to the thumbsticks. So yeah, I'm just kind of looking at this code here. You can see we've got this map stick X that takes the stick X value on stick X and Y, or sorry, stick just X, left and right value. And it maps it from what Apple's IOHID library gives us, which is going to be some kind of unsigned integer, 8-bit integer-ish value from 0 to 255. And all it does is it maps it into a different space. And that space is the space between -1 and 1, where -1 is hard left, 0 is the middle, and then 1 is hard right. So that's kind of the idea here. Is we take that and then we use that to determine what sort of frequency sound to play. All well and good, except we had a crash, and I sort of want to investigate what that was. What I'm guessing it is that we somehow went into some kind of I think we triggered some sort of floating point exception, and so I kind of want to look at what that amounts to. But I have some idea as to what that probably is. So we're going to open that up and just kind of take a look. So we go here, and we're just, unfortunately, I have to keep modifying this Xcode project every time so that it will, properly load the actual game itself. We're not going to spend too much time on this. In fact, I don't really want to spend a ton of time on it. I actually want to get to something else. But I wanted to at least briefly look at it because I don't really want us to really continue with the app crashing or with the game crashing. So that's what we're going to do. So we got this kind of handmade thing here, and we're going to run it. And then I'm actually just going to try and trigger the exception, just see what happens. Okay, so you hear that tone, right? This is so fun. Now I'm going to slam hard left. Okay, and that crashes me. Well, this is what's so great about having the debugger set up in Xcode is it's like I said, we're probably not going to use Xcode for a ton of stuff, but it's actually really great for this in particular because we can be kind of debugging the Mac platform layer inside of this tool, and it's really quite an excellent tool for that purpose. So let's see, arithmetic exception on calculating the period. So I'm guessing that maybe this is like a divide by 0, right? So if you think about it, what we had here was, let's go back up. So, or actually down further here. So we've got this, so our base is going to be 256, right? So the base value for the stick X is 256, and if say for example this is mapped into, well actually yeah, so if remember a hard left is like -1, so what that's going to do is it's going to be -1 times 256 plus 256, which means that we've got a frequency of 0. So that really shouldn't be possible, right? So if the frequency were 0, then we would we'd have a divide by 0 here, and I'm guessing that is what's triggering this arithmetic exception. So instead, I think what we're going to do is we're going to, I'm not, we could try and get it really, really down low if we want to. So maybe, just a really kind of quick, stupid sort of thing we could do is if this is, if the base value is 257, right? Then the lowest that we could possibly go is like 1. Now that, I don't even know if that's an audible tone. I'm guessing it's not, but we'll find out. So let's just kind of build and run again. Just run our build script. All right, and then I'm gonna stay inside the debugger because just in case we trigger another exception. Okay, so you hear that. This is actually really fun. So I don't want to spend too much time with this, but it's really fun. So it's pretty cool. Part of me wants to like make a sound mixer or something for this, just because it's really fun to play with this. So okay, so that's cool. We fixed that. So it seems as though our reasoning was rather sound, right? So we come back here. Yeah, if the base here is like 257, right? Then there's just no possible way that we're gonna ever hit 0 and trigger this, divide by 0 sort of arithmetic exception. So excellent on that one. So we solved that. I'm just gonna put that here and we're save. And I don't know, I'm just gonna do a little bit of cleanup. So there's that. Okay, so we're in a good spot. And now the kind of thing that I really want to talk about is calculating the performance, or rather calculating just straight up the amount of time that it's taking for this thing to go through this loop. Because a game engine is really, if you think about it, and this is something that's kind of covered in Handmade Hero as well, there's really, at a base level, you've got a few things going on. So I'm going to make some shapes. So we've got this part, and that's, we're going to say that is, can I draw some text? We're going to say that's input, okay? And I don't know, maybe I'll make this like much bigger or something, right? Why, Sketch? I like you otherwise, but this is just, okay, so we've got input, right? And okay, so the very first thing that a game engine is supposed to do is on every frame, what it does is it gets some input from something, right? So depending on how it is that you're controlling your game, or however you're controlling your system, it grabs input from something. In this case, we are getting input from a Sony PlayStation controller, right? It could be any controller, or it could be a keyboard, or it could be, I don't know, some kind of other like peripheral device that you yourself invent. Maybe you like hook some electrodes into a banana and you like have like the banana controlling game or something like that. Like that's possible. The idea though is we're getting input from somewhere, right? So that's the first like step of what's going on in a game engine, right? The next step is what we would call kind of the we call it like the update phase. We haven't really done too much. Well, we're kind of doing some stuff with that. So we'll call that update. Okay. And so what is that? Well, what it means is there is some kind of a simulated world that exists in our game. So let's say that Handmade Hero is largely based off of it's largely inspired by the Legend of Zelda, and so the Legend of Zelda. What is the world that Link kind of lives in? I mean, Link sort of lives in this. He lives in this like kind of two-dimensional tile map world. Well, he used to. Now he's like three-dimensional. There's entities that are in that world. There are trees. There are boulders. There are caves. There's a guy that's like going to sell you some bombs. There's Princess Zelda, there's Ganon, there's all these like entities in a world. There's stuff in a world, right? And so the second phase of what goes on in a game engine is we take your input from like your controller or your banana or your VR headset controller thing, whatever thing, keyboard. And what we do is we use that to then update the state of the entities in the world. We say, okay, based on this input, we're gonna now advance the world by a frame, right? We're gonna advance everything by a frame. Okay. So are we doing something like this in this, even at this like rudimentary or base of a level with this platform layer? And the answer to that question, I would say, is yes. And that some of the things that we're doing and what I would now our update phase is a little bit out of order, and that's fine because right now we're just like in a prototyping phase. We don't really care. But I would argue that this offset thing, this offset X here, that's the update phase, right? So we're getting input from the game controller, right? And we're using it to update the state of the world. Now our world is really simple right now. Our world is just it's just a image. It's like a gradient image, this buffer or whatever. And its state thus far is like an offset X and an offset Y. And that's really all that we can control about it. But it's a world nonetheless. If I press right or press down, and the world has some sounds in it. It's got this like tone, I've got like a frequency. So we could even say that the sound frequency is a part of the world, right? And that on each frame update, what we're doing is we're modifying the state of this world. We're modifying this offset based on the input, and we're modifying the frequency of the sound that gets played, right? So okay, well that's cool. Now what's kind of the final phase here? Well, we have render. Okay, so in that case, all we're doing, so render. I'll just say render, right? So now we're rendering. Okay, so what does render mean? Well, it's just a really fancy way of saying like, if I was to explain this to my 5-year-old nephew, I would say we draw a picture, right? So that's all that we're doing, really, or we make some sounds. So we take the input and we update the state of the world, and based on the state of the world, we decide what picture we're going to draw, okay? Or we decide like what kind of sound we're going to make people hear, okay? So, the drawing of the picture, that would be, remember, this is kind of out of order, and we're going to change that. That would be this thing right here, render weird gradient. That's drawing a picture, and guess what? That picture, it takes the offset X and the offset Y. I would argue that right here, this like sound code that we just wrote, that is sound rendering. So we're taking the input, the frequency, and using that to decide what sound to output to the speakers. Okay, so we've got all of those things. Now it's actually really important that with all of these phases in a game engine, that we be able to know how long does this take, right? So I could say something like, how much time, right? For all of this together, because what's going to happen is this together is like a frame, okay? So every frame we're going to input, update, and render. We're going to gather input, update the state of the world, and render. And we want to know how much time did that take, right? Now that's really important because just because of what human beings are. We're sort of these, we kind of like walk around the world and we like look at stuff with our eyes and we perceive things. And we process information with our brains. And it's actually, we want to create something that looks convincing for human beings, right? And so human beings sort of naturally have this like refresh rate in our brains or like a minimum amount of like refresh rate that we have, or that we're like willing to accept as sort of believing that the thing is moving. And roughly speaking, that refresh rate is somewhere around 24 frames per second. Okay, so a lot of films will try and hit something like 24 frames per second. Okay, so what that is like, that's just barely enough to convince the human mind that what it's seeing is real. It's animated. It's enough to convince you that it's not broken, that you're not looking at something that is like standing still, if that makes sense. So it's actually really important that we be able to hit this timing, that we be able to get at least 24 frames per second, right? Because if we can't, then we don't really have something that is convincing to other human beings as a game or as an animation. So we have to at least hit that. And in order to be able to hit that, we need to know how much time did it take to do these three things: to get input, to update the state of the world, the entities, whatever it is, whatever state, and then to draw a picture from it. So how do we do that on a Mac? that is the subject of today's discussion. So actually, I'm just going to minimize this. So to do that on a Mac, we have a few different functions. We have this, let's see, I'm going to look it up. It's this mock absolute time. And mock absolute times, you'll get a bunch of these. Like, I really hate searching for this stuff because it's just always awful. It's funny how like this stupid like Stack Overflow thing is like higher up in the search rankings than the official like kernel documentation from Apple, which sucks. But see, what also sucks is like this is completely useless to us because it's like, okay, well, we call this function, right? Like there's this absolute time function, and we know like we're gonna get something from that. We know that's like a unsigned 64-bit integer. Okay, great, but like now what? Okay, and we also, there's a few other like time functions that we need to do. So what we want to do is we want to measure the time difference per frame. So the first thing that we want to do, I would say, is I want to go up here, and now this is going to be in our just in our main function, and we would want to do it right before we start running, right? And the reason is because if we don't do that, we're going to, well, we're pretty much going to like, we're going to have this stuff like setting up the sound is going to be considered like part of that initial calculation, and it won't be right. So what we want to do is like start it right at the time, like right before we start the game's main run loop. Because if you think about it, we've got this main function right here, and this is our entry point into the game, and all of this stuff is like, it's all set up that we do right before we ever get into the meat of the main run loop, right? So we do all this kind of setup, and then we get here, and now like we're in the main run loop. And so this mock absolute time, I believe that this, so again, you have to kind of like read around a lot, and it's like there's just no good documentation, unfortunately. We know that we get this like unsigned integer 64-bit thing, right? And what that is I'm gathering that it's like some kind of timestamp, right? And so if we say, let's just say like uint64 last counter, what that means is like the last time that we took the timestamp from the computer or from Mach, because this operating system, by the way, this is the Mach operating system. Or rather, Mac OS is based off of this Mach operating system, which is based off of the free Berkeley software, some variant of the free Berkeley software distribution from like back in 2000-ish. So that's kind of where this I don't know how it came to be known as Mach. It was like, I forget. There's some backstory. I don't know, it doesn't really matter, but that's kind of where some of this stuff comes from. It's very like operating system level type stuff. So just for those who are kind of curious. So we have this counter, and remember like uint64, like for all of our different types, we have kind of done our own type variants. So here's this last counter. Now this, we're not going to be able to do anything with this right as it is because we just we don't have the actual libraries. Like we can't really build. Well, let's just try and build it. You'll see. So if I try and build this, we don't have the actual libraries that we need, and so there's no mock absolute time library, and that's because we don't have it. So I'm just going to go and nab that from my other platform layer that I built a while ago. So we need mock init and mock time. So these are just some different include files. Okay, so we're going to use those, and there we go. And so now I'm just going to make sure that we can actually build still. Okay, so now we can build. So we have that function. All right. So yeah, so we're in our main loop here, or we're in the main function, right? And we're going to say, okay, well let's start by saying the last counter is whatever time that we took right before we started the run loop, right? Because this run loop right here, every iteration over this run loop is the same as one of these. It's gathering input, updating the state of the world, and rendering. Okay, and what that is that's like one frame. So every iteration, this is how we're thinking about this engine. Every iteration through this run loop is a single frame, right? And so what we want to know is really at the end of the frame, like right here. So we can say note end of frame, right? So at the end of the frame, what's the time, right? So so at that point we could say let's just say unsigned integer 64 end of frame time, right? So something like that, okay? And now that's also going to be mock absolute time, right? Okay, and now what we would want to do is we would want to say, okay, well, now what is, like, how much time elapsed, right? So we want to get to frames per second, but what we're going to end up starting with is something like a seconds per frame. And now I only know that also, like, this is in nanoseconds. So I only know that because I searched around a bunch and found a bunch of resources. So whatever this uint64 value here, that's going to be like a nanosecond-ish kind of thing. Well, wait, actually no, wait. There's this other transformation that has to happen, but it's in some units. It will be in nanoseconds. So then we want to do is we want to say, okay, well. So we got the last time that we updated the counter, and then we have the end of the frame, right? Okay, well, how much time has passed since then? So we could say, time units per frame, right? And what all that is it's going to be end of frame time minus our last counter, right? Minus the last time. Now on the first time through, we got last counter just right before the top of that while loop, and so that will give us a valid value on that first time through. So we have time units per frame, and then what we're going to do is we're gonna say, okay, well, so now that we know what our time units per frame are, we're going to just say that the last counter now is equal to mock absolute time, right? So we're gonna set this now. We're gonna reset the last counter so that it is it's lined up with, or how do I put this? we're just gonna reset it so that the next time through, we will still have a sense of what the time was, because we're just gonna create this new value right here, and then we're gonna do the subtraction and know how much time has passed per frame. So we always have to update the last counter at the end of the frame. Otherwise, we won't actually know how much time passed in a given frame, right? We would only know, like, if we didn't update it, we would only know, like, how much time has passed since the very beginning when the application launched, which is not really what we want. So, all right, so we got this last counter here. Now, whatever we do here, right, this is like, here is where you print stuff. Or where you print stuff, or or where you get this is where you take your diagnostic that you got from this and you use it for something, right? So this is where you would say, okay, now I know how much time has passed in the frame. I would print that out and I would say, okay, it's like this many seconds per frame or milliseconds per frame. You can also do like a division or something and get how much time has passed since then. Like there's a lot of different things that you can do there. In our case, this kind of brings in this sort of other kind of ugly-ish thing that it just kind of is how the operating system works on a Mac. It's this like mock time-based info thing. So I'm actually just going to go grab that from the other platform layer because it's not super interesting, unfortunately. So yeah, so there's our end counter right here. We've got this, right? So all we need to do is we need to like run this thing once, and then yeah, so we'll use that. I'm actually just going to grab this because I think a lot of it is what we want. Okay, so we've got this mock info. I'm just going to call this like time. So I'm actually just going to call this time base, right? And we've already got the yeah. So we know what this is. We know our end of time. Yeah, and so since we've already done that, yeah, right. So we've got our time base, and then if we say, okay, well, if time base dot denominator equals 0, then that means that we've never. You have to initialize this thing, so that's kind of what this is. And I think eventually we'll just pull this up. Actually, let's do this. I want to pull this up I want to hoist it out of the run loop because there's really no sense for this to be running like more than once. Actually, I think we can just get this time base info once. Because what you do to get the time base, this is like, I don't know, I guess like not every, so this mock time base info thing and this mock time base info data T, it's got two things. It's got a numerator and a denominator. And all that does is it just kind of like, if we take some amount of time and we multiply it by the time base over the time base numerator over the denominator, then we will get nanoseconds. So that's how we know like how many nanoseconds we have. There isn't a ton of documentation as to why this is the way that it is. It just kind of is that way. And it just sort of like I couldn't find any documentation. It's like everybody's like, nope, just use this code, it works. And it's just kind of, I guess, known that, mock time base info, we pass the pointer to this, we pass a pointer to this structure, mock time base info data T. And I guess like different kinds of computers will have different numerators and denominators for that. So something like, MacBook Pro might have a different one than an iPhone would have, or an iPad or whatever. So it's all kind of just dependent on. What I'm guessing is that this like time-based info thing is like it's like a wrapper. It's like kind of like a C wrapper around kind of some sort of intrinsic that's going on in the actual system, and so it will return a time base that's based on what the actual like hardware performance counter is. That's kind of a guess. I'm hoping it's a good guess, but I could be wrong. So and if we also if we hoist this out, then we don't need to like check if it's 0 or anything like that, because we're only going to do it once. So I think that makes a lot of sense. I'm gonna hoist it up out of the while loop. So it's kind of funny because like while I'm going through this, I realized that the first time I went, this is like the true in all kind of software development, is like the first time that you do something, you're not nearly as you don't fully know what you're doing. So it's actually kind of cool to like come back and just for the purpose of like demonstration or just for talking, kind of go over this platform layer again, because I'm actually realizing stuff that I did sort of incorrectly, or that I kind of, like I said, like a lot of this was actually an intro for me to procedural programming, and so I've learned a lot in the last like 10 months, and so there's just things that I probably now wouldn't have done the same way that I would even have done like a few months ago, which is crazy. So that's cool. So we got this like mock time-based info, and so we're just going to get the time-based info. We're going to do that once at the start of the main function, right? So when this thing like first boots up, right? We're doing this once, and then down further here, we're going to use its numerator and its denominator to get the number of nanoseconds that took place. So we could say this is like nanoseconds elapsed, or like we could say this is nanoseconds per frame, right? That's really what that is, and it's not elapsed. It's just time units per frame times time base. I don't know why I'm just gonna put like a thing over there, all right? And then and now all we want to do is like we're going to convert this to like a floating point number, and we're going to, and then so that we can print it out basically. So we're measured seconds per frame, I guess. Like I'm just going to say it's like seconds per frame, right? And then we're just going to cast to a real 32 nanoseconds times this. All this is doing is it's like saying, because nanoseconds is going to be a large number by a factor of 10 to the ninth, right? So if we multiply it by a factor of 10 to the negative ninth, then we effectively turn it to seconds. That's the idea. And now you may want to do this as like milliseconds. So if you want to do milliseconds, I think it's just like 10 e negative 6. So milliseconds can be pretty useful, because if you know like certain frame timings, for example, you know that a single frame is, if we're targeting like 30 seconds per, or 30 frames per second, then you know that your time budget per frame is like 33.333 repeating milliseconds per frame. And like if you're hitting 60, then it's like you've got 16.6 repeating whatever. So that's just kind of something you'll know what these numbers are, and you'll know if you're at least hitting them. So we're gonna go frames per second. Okay, so this is not just nanoseconds; it's nanoseconds per frame, right? And then just to get frames per second, we just do 1 over, right? So that's just inverting the units, right? So if we have frames per second and we divide by seconds per frame, or if we take seconds per frame and we like flip it around by doing 1 over that, then we get frames per second. That's kind of the idea. And then we probably would want to print that out. So that's like it. We'll just use NSLog. And oh gosh, I forget. I don't know all these like format specifiers by heart. %F, right? Okay. So we're going to use %F. And then that takes frames, right? That takes frames per second, right? And for any of you like wondering like why all of this like uppercase, C-ish kind of, because like a lot of people are really used to having a certain kind of thing. certain kind of like style. I'm actually just, like I said, a lot of this, you may choose to like make these, you know, like lowercase or whatever. That's fine. I'm just trying to do this as much in the spirit of Handmade Hero as I can. And so that, you know, Casey uses this kind of like Chris Hecker sort of every instance or every like variable is like uppercase thing. And it makes a lot of sense actually, like in C, and most of what we're doing is just C. So like this distinction between like what's a class and what's like a member variable and what's this thing or that thing or the other. Much of the kind of programming we're actually going to be doing here isn't even going to be concerned with those higher level concepts that you might find in, say, Objective-C or any of those other or C++ or any of the higher level languages. So that is just kind of explaining a little bit of what's going on there. So we should be able to now, in theory, see what our frames per second is or looks like. And we're actually going to use Xcode for that. So I'm going to build this. All right. And then we're going to run it in Xcode. And it should just pop up in this like dialog or in this like in this box right over here. So I'm going to run. Okay. And you can see it, right? So you can see that we're hitting like, and now notice that this is highly variable, right? So, you know, 75, 76, 78, 79, and then sometimes it like, you know, like this will happen here and we'll hit like, you know, like 38 for some reason. And that's usually something like the operating system comes in and like does some extra work or whatever. The important thing to note is that this is very inconsistent. So first of all, the reason that we have any kind of smooth animation, like first of all, we have smooth sound, we have smooth animation. We know that because when we actually play, or like when I you know press buttons on this, the buffer moves, right, and I can adjust the sound with my analog stick, right? So we know that we're getting, so we know that the thing is like responsive enough. Like I don't feel like this is juddering when I don't feel like it's juddering when I press down, or that it's like not a fast enough frame rate. It's clearly a fast enough frame rate, right? And our output here shows that it's a fast enough frame rate. Now, if you were to say, so let's run this again. If you were to resize this and like say only render this or like this square right here, like let's just say in theory that you were going to do that. What you would notice is that this frames per second goes way up. It goes up to, like I've played around with this. You can play around with it too if you want. You'll notice that this frames per second goes way up. And the reason is, going back to this diagram, this is kind of something Jonathan Blow talks about a lot. And it's sort of this like, it's this truth of game programming that is not often well enough recognized. But this right here, these three things, input, update, and render, that's in order of expensiveness. God, that I hate. This pencil is so. Okay, I'll say expense. So as we go through each of these phases, the cost in terms of processing power goes way up by several factors. So just gathering input from a controller is the cheapest thing that you can do, is often the cheapest thing that games do. Because if you think about it, it's like, oh, we get some stuff from this PlayStation controller, we pull it, and we update like a Boolean variable, or we take this like, we take the stick left and right, which is kind of like this unsigned 8-bit integer thing, and we map it into this float space. What's that, like one operation or like a few operations? It's cheap, pretty cheap. Updating the state of the world starts to get a little bit more complicated. And in this case, because like right now we're only doing the platform layer, there really isn't much of a world to update, so it's about as cheap as gathering input, but this starts to get more expensive. Rendering is the most expensive thing that a game engine will do, which is why if you just make the size, actually let's run a little experiment just so you can see what I mean. Because what I want to do is, I think we actually have, so we do have this this global render width and global render height. Like, what if we decided, I'm just gonna actually, I'm gonna comment it out, and what I'm gonna do is I'm gonna go, I don't know, like maybe this is like 320 by 480 now or something. Like this is like an iPhone screen. I'm just an old iPhone screen. An iPhone from when I first started doing iPhone app development. Okay, so I'm gonna build this thing. All right, so we got that, and all right. So what we're gonna do is now it's gonna draw a different window. So it's gonna draw something like an iPhone screen, right? So this is like an old like iPhone 4. Now look at this crazy shit. I mean, we're not supposed to be cursing, okay? But like, look at this. Like, we just like bumped our frames per second up to like 340 something odd. Like, that's crazy, right? And the reason that we did that is because we just dramatically reduced the cost of the most expensive part of the pipeline, which is rendering, right? So what we did is we said, oh, we're actually going to render much less than what we were rendering. We were rendering this like 1024 by 768 window, right? And that was fine. Like we were above 24 frames per second. We were above like the threshold for what a human being can perceive, can perceive as animation, which is why we were successfully at, why we successfully kind of like hit, like 80 or whatever. But when we dramatically reduced the cost of rendering, we got to like some pretty insanely high, frame rates here, frames per second. And so that all kind of comes down to this like fundamental truth about the cost of certain operations. And so if you starting to think about, much of the direction that modern chip design has gone in lately has been in trying to figure out ways to make this part faster. So that's why your computer has a GPU unit on it, right? Is because what we want to do is we want to make some kind of special purpose unit, something that is designed specifically to do certain kinds of floating point math really, really freaking fast, so that we spend less time here, right? So what we're doing is we're just basically like, as anybody that's optimizing something well would do, you take the most expensive thing and you say, okay, how can we make that better? And then you make that better, right? So that's kind of what this is all about here. Is we say, okay, well, gosh, rendering is really expensive. And if we're looking at this code here, so it's also important to note, so the bulk of the cost of what we're doing comes from a few lines of code, and it's this right here. This is the costliest thing that this app does right now, okay? And it's extremely costly. What this is basically doing is it's software rendering. It's not hardware rendering, it's software rendering. So instead of using the GPU, graphics processing unit, it's using the CPU, central processing unit, a more general purpose type of piece of hardware to do graphics, right? So we obviously I'm gonna put a to-do here, and it's just simple. Replace this with calls to hardware, replace this with hardware rendering, right? And so if we instead replace all this like software rendering with calls to graphics APIs that then talk to the GPU, then it's going to dramatically reduce the cost of all this rendering that we're doing, which is going to make us more able to render more advanced graphics. It's also going to make us more able to hit that kind of time, frame timing. You imagine if we, so note this, so our, what I'm kind of curious here is just kind of a fun experiment, right? I don't even think it's possible for us to go full screen. I'm not even sure I want to try with like OBS on. I don't even think it's possible for us to go full screen on this Mac using the software renderer. I think it would just completely tank the frame rate. I think the thing would just it would stall out. We would get well below 30 frames a second. If the operating system came in and like did any kind of extra work or like tied up the CPU in any sort of like way, we would just be hosed. And so this is just to kind of give you a sense of sort of what the direction is. It's like, yeah, right now, like, while we're sort of in this like prototyping phase very early on, we can sort of use the software renderer, but ultimately we really do want to move towards GPU. So whether that's OpenGL or whether that's Metal, something that interfaces with the actual GPU on the computer is going to give us a huge boost in, remember, the most expensive part of a game engine, this rendering phase here. So, and we will also want to hit a certain time, frame timing. Right now what we have is kind of the base of being able to hit a particular frame timing. Now that we know how much time it's taking to render, to do one pass through this engine kind of while loop, now that we know how much time that takes, we can sort of push that into the next step, which is saying, okay, now that we know how long that takes, let's try and actually let's intentionally hit a specific timing. Well, we're not going to do that right away. We're actually going to do next in the next sort of video. We're going to start to talk about kind of cross-platform architecture, and so the idea is we want to make it so that this Mac OS part is really a very, very small part of the actual game library. We don't want to couple. We don't want the game the game code itself to be too tied to any particular platform. In spite of what Apple probably wants. I don't think they want that either, because what they want to get like the major publishers on their platform, and so if having the people you want something manageable where you want to be able to write your game logic once, right? And then have that same game logic available on different platforms. You don't want to have to rewrite your game logic multiple times for different, just to support another platform. Like, that's silly. That's like a lot of rework. And so the idea, kind of moving to the next thing, remember we call this a platform layer, right? And so what a platform layer is it's just this like teeny tiny thing on top of that is platform specific, that's on top of a game, and it calls into the game, asks the game for some sound, a picture to draw, and the game gives it back, and then the platform layer like puts the picture on the screen, and then plays the sound. And so the idea though is that we're going to start moving more towards a cross-platform architecture. And actually, what's really cool about this is it kind of ties into sort of the purpose of the series. The purpose of the series is to get you to a place where you've got the game library set up, or rather you've got the Mac platform layer set up, and then what you can do is you can actually follow the series completely. So, and that's because the actual game part, the game code, is completely separate. It's isolated from any particular platform that it's running on. So by about day 25 or so, once the platform layer is complete, you can actually just follow the series like straight up, more or less. You can follow the series just as if you were running on the same computer that Casey's running on. And the reason is because at that point in the series, he's actually working on a fully like cross-platform game. So the game library is totally separate. You just follow along. You just like, it's the same language. It's all C. And so you just, follow along with the series. There's a few things that are a bit different. Like I think there's like one difference is like the the color display, like the bitmap display endianness is a little bit different on the Mac as opposed to on the PC. So when it comes to like loading bitmaps and like drawing pixels or whatever, like that's a little bit different. That's kind of like platform based. But that's like if what you could do is you could just pass in a flag like saying, hey, this is the endianness of my system or whatever, and then you could like you choose different bit operations. It would still stay cross-platform. So it's like a slight difference, but it's not like a big thing. I've been able to just like follow along for the most part, aside from like a few parts where like we load bitmaps differently, and I'll actually go over some of those parts as well just to make it easier for people to follow along, because that's the goal. But yeah, aside from that, that's what we're going to cover next. So appreciate your time and enjoy this lovely day, and it was a pleasure programming with you.